Hello, and welcome to episode 1 of Designing the Anthro. My name is Ian, and today we will be going over the work that I have done so far in designing the knee and elbow joints, as well as some of the design theory behind the Anthro and why we want to incorporate those features in a robot. So, without any further ado, let's get started. So, gonna open up Fusion 360 here. And as you can see, what's on screen right now is the uh, bearing retainer for the knee joint. Now, the reason behind this design is I wanted to go with as much of a modular design for the robot as possible. So as you will see with how the knee and elbows have been designed, they incorporate magnets to hold everything together, as opposed to using, say, nuts and bolts for most of the parts. So, right now, you can see the retainer on screen. It's designed to fit two large bearings on each side, and the center has been left open in the middle so that a timing belt can be run through from a motor or some other form of actuator to drive the actual shaft in the center here. And that shaft is comprised of two components, two halves of the lower knee. Right here, you can see that it can fit a 30 millimeter neodymium magnet, and this portion here will connect to the rest of the lower leg. Now you have two of those parts that get inserted, one from the right and one from the left side, and they meet right in the middle here. And the magnet will hold the two halves together and also somewhat hold them in sync when the lower leg rotates. Now, one issue I've run into is sometimes they can become unsynchronized. Of course, the rest of the lower leg will be held together by more magnets and by 4 or 5 nuts and bolts. We want to reduce the amount of nuts and bolts we use in the design as much as possible. So for that reason, we're using magnets wherever we can. We won't be able to completely eliminate using conventional fasteners, but we'll do without them wherever we can. Now moving on to the elbow here, it's very similar to the knee, except it doesn't have a hollow gap in the middle to allow it to retain a smaller form factor for use in the elbows and ankles. So instead we have two of the exact same bearings that get inserted onto either side, and then of course a very similar system as to what the knee uses. Again, same 30 millimeter diameter neodymium magnet, and both halves will meet in the middle. Now, one problem I've already seen with this design right off the bat is we don't really have many options for where we can run a belt on this elbow slash ankle one in particular. And the problem with that is if we wanted to drive the entire thing, we would have to run a timing belt or antagonistic cable system around each side of the elbow or ankle, and that's not really ideal. So one thing I want to do, and I will modify the design for both of them, is where you can see this gap in the center here. That is where the portion that will make up the lower leg will actually go to. So instead what you'll have is you'll have these two parts that retain the bearing. Those two will be rotated the other way so that this disc in the center here will be on the outer part, and you'll insert the bearing from the inside going this way. And essentially all you'll have to do then is you'll insert this hollow donut type shape that more or less looks like this, except there isn't this plastic shaft with a magnet holder on it. Instead what you'll have is you'll just have a hollow hole in the middle there, and then this rectangular portion will still exist. And what you'll do essentially is you'll slide it in between these two halves, and you'll insert a locking shaft type design that is more or less this part, but without this rectangular end on it. And it'll still have the magnet in it. and it'll act as a shaft. All the load for the robot will be placed on the shaft, supported by the two bearings still, and it will still allow that center part to rotate freely. The advantage is, through the center here, right here, we can run a timing belt through, and we can actually use a fairly thick timing belt. The actual amount of clearance we have here, I believe, is 14 millimeters. Yeah, 14 millimeters. So that gives us plenty of space to work with. We're probably going to use a standard GT2 timing belt because they're pretty common, they're pretty inexpensive. We might just double up on two of them, for example. And we'll run it through the center. It'll run right to the back here. We'll carve a hole in the back of this, and we'll run the belt through there. And that'll go up towards the thigh. So those are some changes I want to do to the knee and the elbow design. Obviously not tonight because it's 12:30 in the morning where I am, so it's a little bit late. But in in episode 2, we're gonna do that live, shall we say? But more or less in this video, I just want to address that issue so far, and I am going to release a video here shortly on YouTube with these existing designs I have so far. Um, you know, show you the designs in person, how they were supposed to work, and generally how the magnet system works, because that is pretty much going to stay the same. We're just changing how the bearings are held in, and going from two moving parts on this thing to just one in the middle. Helps slim it down a little more too, and you'll see why in a second, because I'm going to pull up some reference images on the screen, and more or less it's going to show what our end goal is. So the first reference image here, this anatomical image of the human skeleton. Now pay special attention to the knee joint here, right to where the knee is. As we can see, it's more or less straight down from the knee all the way down to where the ankle would be. However, from the knee up towards the pelvis, we can see that the femur is actually angled up. And then we have all this void space here, the thick fleshy part of the thigh. That's all dead space compared to where the actual bone is. Now, we're not just going to have a singular bone or piece of tubing. In our skeletal structure, we're going to be using multiple carbon fiber tubes. Keep it lightweight, but again, keep it nice and strong. Instead, we're going to fill this dead space here with potentially an actuator or motor and gearbox driving the timing belt that will run into the knee and move the lower leg. But we want to keep it as close as possible, though. We want to reduce the backlash. We want to reduce the length of the belt that we actually need. Some designs I've seen in robots, they have a timing belt that runs all the way from a motor located in the pelvis all the way down to the knee and even all the way down to the ankle. It's a lot more chance for something to go wrong there. If we keep it nice and close to the actual joint, less can go wrong. Now this also means that we have the possibility of keeping the controller board for the motor nice and close to it so we don't have any signal loss. We can keep a power supply or two, batteries for example, inside the thigh as well, which means that we have more room available in the pelvic region and in the actual torso to either fit computing systems or more power supplies. So we don't have to have the entire torso just full of motors to drive the rest of the robot. Now, another design choice that we've elected to go with, as you can see in the human skeleton, it's a plantigrade design, which means we have our hips and our standard hip joint and pelvic configuration, if you will, running down to your knees, runs down to your ankle, and then your foot. And it's a large flat foot, heel to toe walking, etc. What we've elected to go with is to keep everything from the knee above to be the exact same. However, everything from the knee below is going to be slightly different. We're not going to be using a plantigrade design in our first model of the Anthro, so we're going to be doing something a little different. I found this reference image online, and it shows a digitigrade biped configuration. Now the way this works is, again, everything from the knee up is the exact same as you would find in a human, for example. However, everything from the knee lower is slightly different. So this time, how it looks is it's as if the ankle was lifted higher, and it's located halfway in the middle of the lower leg, right? So you're basically breaking the lower leg into two separate parts. But as you can see in this rightmost reference image here, it looks like this area here, if you can kind of see where the mouse cursor is, it looks like that would serve as a good ankle joint. Now, if we were to break the lower leg into two smaller lower legs, if you will, it allows us to have more control of the positioning, the gait of our robot, and also allows us to then spread the weight across a larger area. So balancing the robot, although it's not going to be done conventionally compared to plant-degrade bipeds, um, I honestly believe that a digitigrade configuration um, will be a unique challenge, and will also allow us to gain some slight height advantages in some areas, and also some agility advantages as well. Now, with regards to having less surface area compared to a plantigrade to spread weight along on the ground, what we're going to do is just have larger feet with larger toes, if you will, and that's kind of the design we're going to be going for. So it's going to be interesting to say the least, but that's what we're going to be going for in our design. Now, with regards going back to the design of the knee and the design of the elbow/ankle joints, um, how are we going to go about installing a pulley system for it? Now, the timing belt run to an actuator won't be an issue. GT2 pulleys, for example, the same pulleys you'd find on a 3D printer, they're pretty common. And they're pretty easy to get, pre-machined and everything. But what about this part here? Highlighted in blue, that's the shaft that we're going to be looking for. So how are we going to drive it? Right? If we were to stick with this design, if not, if we're going with the hollow donut design, how are we going to drive this thing? Well, around this part here highlighted in blue, we can place, don't mind this rectangular part. We'll get rid of that after. But say, for example, that wasn't there, right? We just had this part and it was a donut in the middle. I'm not going to do it right now, but next video we will. So this right here, right, this right here, what we can do is we can actually put a GT2 pulley a profile around it for the belt. Now how we're going to do that is I found this really nice tool for Fusion 360, and I'll link it in the description of the YouTube video. But I believe it's made by Com3. I'll correct myself if I'm wrong. Here, actually, let me just check a reference here. No, made by MRC on Thingiverse. And it's a GT2 belt generator for Fusion 360. Now, I already have it loaded up here. So it looks like this. So essentially, we can create a GT2 belt and 3D print it out of flexible filament. Now, we're not going to do that. Instead, what we're going to do is we can modify the actual parameters and the actual sizing of the belt that we want for the diameter. Keep the pitch and everything the same for the teeth. And what I'll do is I'll overlay this on top of that cylindrical portion of the knee joint there along this part, and I'll just subtract from it. So it'll leave behind the profile that the pulley can go around. And then that way, all we have to do is fit a pulley around this, run it back through our bearing retainer down the center here, and boom, we're in business. Now we can actually drive our knee joint, no problem. Now we might need to add some idler pulleys in these parts here, and that's just to, or more or less along the top here. And that's just to, reduce friction and make sure it's not rubbing up against the plastic or anything wearing down. But that's easy enough to make some modifications for and fix. So that's more or less all I want to talk about today for the first episode. Again, this video will be uploaded onto YouTube after streaming on Twitch, just so we have area for it to act as a reference. So that's good. So we will see you all in the next episode. And of course, more videos of, well, a video of this, um, the printed bearing assembly here, and like the knee and elbow joints that I've already made. I'll upload a video for that soon just to show you how the magnetic system works, and then of course the shortfalls with the design I have now. And then in the episode 2 of this series, we will actually be doing the modifications live. So I hope to see you all then. Take care.